Hi folks! The following video is a new type of mechanistic experiment called a Hammett plot. Hammett plots are a type of substituent effect. A substituent effect is a measure of the way in which the reactivity of a molecule changes as you change substituents on it. Substituent effects are a way of testing for changes in charges by changing functional groups. For example, switching out a hydrogen for an electron donating group or an electron withdrawing group, and seeing how that affects an equilibrium or a rate. I want to compare substituent effects to isotope effects. In the case of isotope effects, you're usually swapping out a hydrogen for a deuterium, whereas for substituent effects, you're swapping out a hydrogen for some other group, X. For isotope effects, changing out a hydrogen for a deuterium does not change the mechanism of the reaction. It can change the rate, but it doesn't change the mechanism itself. When you're thinking about substituent effects, sometimes changing out a hydrogen for a different substituent can actually change the mechanism. By saying that for isotope effects there is no change in mechanism, I mean that it has the same energy surface for hydrogen versus deuterium for the reaction coordinate diagram. Whereas if you had a substituent effect that happened to have a change in mechanism due to that effect, you could change your potential energy surface, or what your reaction coordinate diagram would look like. Hammett plots exploit substituent effects, and they're a way to evaluate how a reaction mechanism varies as you change out the electronics by changing these substituents. The baseline reaction to which we'll compare all other Hammett plots is substituent effects for benzoic acid acidities. So imagine you have a para-substituted benzoic acid, where X is your substituent that you're changing. The reaction is looking at this benzoic acid reacting with water to have an acid-base reaction leading to a benzoate anion and hydronium cation. We'll call the equilibrium constant for the substituent X big Kx. For all different substituents X that you want to study, you would compare the equilibrium constant for that substituent X to the equilibrium constant where X is a hydrogen. You would take the ratio of these equilibrium constants, take the log of that, and call that value sigma for X. Sigma is a measure of how that substituent donates or withdraws electron density from the aromatic ring. If sigma is greater than 0, that means that the equilibrium constant for your substituent X is greater than the equilibrium constant where X is hydrogen, and that will be the case if your benzoate anion is more stable with the X group attached to it than if there's a hydrogen at the X position. This will be the case where sigma is greater than 0 when X is an electron withdrawing group, pulling electron density toward itself to stabilize negative charge. If instead the sigma value is less than 0, this equilibrium constant for the X substituent is smaller than that for hydrogen, and that will be the case when this negative charge is not stable. For example, if you had an electron donating group on your aromatic ring at the X position, that would put more electron density into the aromatic ring, which would destabilize the negative charge, disfavoring the product side. Here's a table of some common sigma values for benzoic acid derivatives, where the X group is at the para position relative to the carboxylic acid. There are two general classes of substituents here. For ones with negative values for sigma, that means that the substituted benzoic acid with the X substituent is less acidic than the benzoic acid by itself. And this will be the case if you have electron donating groups. These could donate electron density to the ring, either through resonance or induction. Substituents will have positive sigma values if the substituted benzoic acid derivative is more acidic than benzoic acid by itself. And this will be the case when X substituents are electron withdrawing, either through resonance or induction. I want to show what resonance effects would look like for an electron donating group compared to an electron withdrawing group. NH2 is considered an electron donating group because it can donate electron density toward the ring using its lone pair. In one of the other resonance forms, nitrogen has acquired a positive charge, and the carbon of the aromatic ring attached to the carboxylate group has a lone pair and a negative charge. This resonance donation of electron density destabilizes the conjugate base by placing negative charges close to each other. In the example of the ketone substituted molecule, you can draw resonance where you're bringing electron density toward the ketone side of the molecule. One of the resonance structures you could draw would place a positive charge adjacent to the negative charge of the carboxylate. Having this type of resonance is favorable because you get positive and negative charges close to each other. So the electron withdrawing ketone group stabilizes the conjugate base, the carboxylate anion. So far I've just been talking about the equilibrium for benzoic acid and its substituted derivatives itself, but we can use this benchmark reaction to compare other equilibria too. For example, let's consider a closely related derivative. The only difference here is that I have a CH2 group between the carboxylic acid and the aromatic ring. So this is a new equilibrium of interest, and we want to consider what effect does the X substituent at the para position have on the equilibrium between the carboxylic acid and water, and then the conjugate base and conjugate acid. Let's consider you performed this equilibrium reaction 5 times with different X substituents. For reference, these are the sigma values for benzoic acid, our benchmark reaction, and not our actual reaction of interest here. What you would do is measure equilibrium constants for all of these 5 different X values, and you would take your equilibrium constant for an X group and to divide that for the equilibrium constant where X is hydrogen. These are the experimentally determined values. Then the last thing you would do for your new reaction of interest is take the log value of this equilibrium constant ratio. Here I've done the math for you. For the new reaction of interest, we're going to use an equation where we have the log of the ratio of equilibrium constants for X or hydrogen equal to a parameter I'll call rho times sigma. What you would do is you would plot your values for the log of the equilibrium constants for your new reaction versus the sigma values for benzoic acid. Here I'm imagining those 5 data points from my 5 experiments from the previous page. I would fit this data to a line and measure the slope. I'm going to call the slope rho, and in this case that I gave you for the reaction up above, the slope is positive 0.55. This rho for your reaction of interest is a measure of the substituent effect for the para-X group relative to that for the benzoic acid derivative itself. So essentially, what is our substituent effect for our molecule of interest compared to that for the benzoic acid? For the original benzoic acid series, this rho is +1, and we're comparing our experimentally determined plus 0.55 value to 1. I want to tell you about how to interpret this rho slope parameter value. Here I'm showing the axes of the Hammett plot, the log of the equilibrium constants versus sigma. Groups with electron donating groups are going to have smaller or negative sigma values, and electron withdrawing groups better stabilize the negative charge, giving rise to larger positive sigma values. So as I mentioned before, for benzoic acids themselves, the slope, or rho, is +1. So one scenario is, what if rho for your reaction of interest is greater than +1? This will indicate that your reaction or equilibrium is building up negative charge close to the aromatic ring. And because your slope is greater than that for benzoic acid itself, that means that your reaction is more sensitive to substituent effects than benzoic acid itself is. So you need a smaller change in sigma value to cause a greater change in equilibrium constant. Another scenario is, what if your reaction of interest has a rho slope value between 0 and +1? This will occur if your reaction is still building up negative charge close to the aromatic ring, but because your slope is less than that for benzoic acid, that means that your reaction of interest is less sensitive to substituent effects than benzoic acid is itself. Changing the substituent has a smaller effect on the equilibrium constant in this case. A third scenario is, what if rho for your reaction of interest is about 0? This would look like a flat line in a Hammett plot. In this case, you would say that there is no substituent effect. As you vary your X group, making it electron donating or electron withdrawing, it is not affecting the equilibrium constant. And this will be the case if near your aromatic ring, you have no change in charge, either in your equilibrium or, when we'll talk about kinetics soon, in your rate determining step. And a final scenario is, what if rho, the slope of the Hammett plot for your reaction of interest, what if it has a slope that is negative, less than 0? This will be the case if positive charge is developing in your reaction near the aromatic ring. In this case, the product side of your equilibrium would be favored if you had electron donating groups to stabilize positive charges, or your equilibrium would be disfavored as you go to electron withdrawing groups, which are destabilizing to positive charges that are developing. I want to show you 3 examples of chemical equilibria and their rho values, and a little bit about how I would interpret these. The first equilibria involves what are known as phenols, OH group substituted aromatic rings, where here as well we have an X para-substituent relative to that alcohol group. We're looking at the equilibrium between this molecule and water to form the conjugate base as well as hydronium. The rho, the slope of the Hammett plot, is positive 2.26 for this equilibrium. This indicates that there is negative charge building up near the aromatic ring in this equilibrium, which makes sense because we see an oxygen with a negative charge directly attached to the aromatic ring. This equilibrium is more sensitive than the benzoic acid case, because in this case the negative charge is directly connected to the aromatic ring, and therefore the substituent X has a greater effect, in this case, for this equilibrium, compared to our original benchmark reaction. Instead, let's consider X substituents that are para to an NH2 group. I would call these aniline derivatives. We could look at how this base could react with hydronium to generate a cationic ammonium conjugate acid and water as a conjugate base. Rho, the slope of the Hammett plot, is negative 3.19 for this equilibrium. The fact that rho is negative means that positive charge is developing near the aromatic ring. And we can see this because the nitrogen has a positive charge on it in the product side. Let's consider if we had very similar molecules, but we just inserted a CH2 group between the NH2 and the aromatic ring. We could think about how would this equilibrium compare to that where the nitrogen is directly connected to the aromatic ring. In this case, rho as well is still negative, but it is negative 1.05. compared to the negative 3.19 value from before. The fact that rho is negative indicates that positive charge is building up, which we see in this cationic nitrogen of our molecule, but the fact that the magnitude of rho is less negative in this case indicates that this substituent effect is not as potent as it was in the previous example. And this is the case because the positive charge that's developing is one position removed from the aromatic ring. So the X substituent is further away from the developing positive charge, and it has a smaller effect on the equilibrium constant, resulting in a rho value that is less negative. So far, I've only discussed Hammett plots for equilibria, which is a thermodynamic measurement. You can also use Hammett plots to investigate and compare reaction rates in the realm of kinetics. For the realm of thermodynamics, you would be looking at how the log of the ratio of equilibrium constants relates to the slope rho and the sigma value from the benchmark benzoic acid case. For the kinetic variation on the Hammett plot, you would be looking at log values for the ratio of rate constants, where you're taking the rate constant with your X substituent and dividing it by the rate constant with hydrogen in its place. Hammett plots in the realm of thermodynamics will tell you about charge buildup in the product side of an equilibrium. For the kinetic variation of the Hammett plot, you'll be learning about charge buildup at the rate-determining transition state of your reaction instead. What you would be doing in the lab in the case of the thermodynamics case is you would be measuring equilibrium constants and then plotting your log of the ratio of the equilibrium constant for X versus that of hydrogen versus the sigma value from that table that I gave you earlier for benzoic acid. Fit it to a line and determine rho, the slope. The kinetic situation is very similar. The only difference is that instead of equilibrium constants, you would be measuring rate constants, and then you would be plotting the log of the rate constant for a given substituent X divided by the rate constant for hydrogen. In the realm of kinetics, I want to discuss SN2 compared to SN1 reactions and how rho values differ for these two different mechanisms. For the SN2 mechanism, rate constants have been measured for the following alkyl halides, where you have a primary and benzylic alkyl chloride, and you have different substituents X at the para position. The nucleophile in this case is water, and after a proton transfer, The products are an alcohol and HCl. The experimentally determined ρ value is negative 1.31. The fact that it's negative indicates that there's positive charge building up at the transition state. And the fact that it's a fairly small negative number indicates that there's not a ton of positive charge building up. You could see why this is the case by drawing out the SN2 transition state. The alpha carbon is losing its bond to chloride at the same time that it's gaining its bond to the incoming oxygen nucleophile. Chloride is developing a negative charge, oxygen is developing a positive charge, and carbon has a partial positive charge at the transition state. Because ρ is around -1, there is not too much partial positive charge developing on carbon at this transition state. In contrast, let's consider a tertiary alkyl halide, where I've just added 2 methyl substituents at the benzylic position. This changes the mechanism to favor SN1, a multi-step mechanism instead. The ρ value determined for this series of reagents is negative 4.48, so negative indicating that positive charge is building up near the aromatic ring at the transition state, and the fact that it is more negative than the previous case indicates that there is more positive charge developing at the transition state for this reaction compared to the SN2 case we saw previously. We can see why this would be the case by evaluating the carbocation formation step, the rate-determining step of the SN1 mechanism. In the transition state, a loss of leaving group is occurring, the carbon-chlorine bond is breaking. Because this reaction step is endergonic, the transition state strongly resembles the carbocation intermediate. So there is a lot of partial positive charge on carbon at this transition state. The substituent X, whether it's electron donating or electron withdrawing, has a large influence on reaction rates, giving us a large magnitude for ρ, because we have so much partial positive charge buildup so close to the aromatic ring. Alright, so in summary, today I introduced the idea of substituent effects, where we're changing out a hydrogen for another substituent that is not just a deuterium. I talked about the tool of the Hammett plot, which uses benzoic acid equilibria as a benchmarking value, and then you're looking at changes in positive charge or negative charge for a reaction of interest relative to this benchmark value. This is a powerful mechanistic tool that can be used to evaluate chemical equilibria or rates and transition states. That's it for this video. I will see you in class.